The next thing we're going to talk about is the coefficient of determination. So the graph alongside illustrates the residual sum of squares in black. Okay, so we've talked about that's the distance from the given y value to the y value found from the model, and then we square that. Okay, so that value is the variation in y that is not explained by the model. Okay, so it makes sense that this is how far away from the model it is. So that variation can't be explained by the model because those points don't fit the model. Okay, so in this sense, as we look at it, the equation that we're given is a line. So these sum of the squared residuals, which is what we've been finding, okay, these residuals are the little black pieces, and it's how far each of these blue points is from the model that we're given. Okay, so it's how far away from the model are each of those blue points. Now, the next piece is called the total sum of squares. So what the total sum of squares is it's the difference between the y values and the mean of the y values. So instead of talking about the y values from the model, now we're talking about the mean. So if we took all of those y values, added them up, and divided by the number of values, that would be the mean. And that's shown here in this red line. And so it's a constant because that mean value isn't going to change. So it's not a model, it's just one value. Now, from there, the total sum of squares, we go from the point up to that red line, and from the point up to that red line. This one, I'm going down, up, down, down, down. So it's how far away from that average am I? So if we break down that formula, this is the given y value minus the mean. We square it, and then we add them all up. Okay, so the only difference from what we were doing before is instead of using the model to get that y value, we're using the mean. So the total sum of squares is the variance in the y values. And so it's the total variation in y. So it's how much y itself is changing off of the mean. So if we were to take the fraction of the residuals divided by the total, that gives us the proportion of variation that's not explained by the model. So out of the total variation, okay, so that's the bottom, from that mean, if we then put that sum of the squared residuals on top, that's the part of the variation, the proportion, that's not explained by the model. So if we take 1 minus that value, that's the proportion of the variation that is explained by the model. Okay, so the coefficient of determination is what we just found, and that is the proportion of the variation that is explained by the model. So the model can explain a certain percentage of the variation in the values. Then what's left over can't be explained by the model. Okay, so there is some, in life, in math, there's some things that we can't explain where the variation comes from. And that's what this is telling us, that the proportion of the variation that is explained by the model is what we call the coefficient of determination. The coefficient of determination is r squared, and it's this formula up here, the 1 minus the sum of the squared residuals divided by the total sum of squares. So we can find r squared using technology. Okay, so certain models, when you do them in the graphing calculator, they will give you an r squared value. Or if it's linear and we're given an r value, okay, if it's linear, this is called, the r value is Pearson's product moment correlation coefficient. We talked about that in a previous lesson. We can simply square this value. So if it's linear, okay, If it's linear, r squared is equal to r squared, okay? But that really only works for linear because Pearson's product moment correlation coefficient is only for linear models. For single variable linear regression, capital R squared equals lowercase r squared. But for multivariable regressions, there are other ways of calculating our capital R squared, so it is not always equal to lowercase r squared. In this course, it is always true that they equal each other. So if you look up multivariable regressions, so that's when you have an x and two y's, and then you're doing something with that. We don't do that in this course, so you don't have to worry about it. So if you're doing linear regression, you're only going to have one x and one y, and so therefore it's going to be true that capital R squared is equal to lowercase r squared. In your math future, you may take a course where you do more in-depth statistics where this is not the case. So we just want to give you this like little heads up that there is a time in math when this doesn't work out. But for pretty much what you're going to do now, this is all you need to worry about. Capital R squared is equal to lowercase r squared. So the interpretation of the coefficient of determination. So if there is a causal relationship, then r squared indicates the degree to which the change in the independent variable explains the change in the dependent variable. So for example, an investigation into many different brands of muesli found that there is a strong positive correlation between the variables fat content and kilojoule content. It was found that R is approximately 0.862 and R squared was approximately 0.743. So in this case, fat and calories, kilojoules, calories, okay, this is European. We just tend to think of them as calories here. But kilojoule is a measure of energy, so fat turns into energy, and we tend to think of calories as energy in our normal, like day-to-day living. But so what that's saying is, and we know from our experiences that the more fat something has, the more calories it has because fat and calories are related through a causal relationship. Okay, not everything we study is going to have a causal relationship, but in this case, there is a causal relationship. Okay, the more fat, the more calories, the more energy. Okay, so an interpretation of this r squared value is that, so r squared was 0.743, which turns into 74.3%. So we say 74.3% of the variation in the kilojoule content of muesli can be explained by the variation in fat content in the muesli. So in this case, we assume that 25.7% of the variation in the kilojoule content in muesli can be explained by other factors. Okay, so there's other things that go into the kilojoules or the calories and the amount of energy that you can get out of a food source. So it's not just the fat, there's also other things. Like we know from our experience that sugar factors in or carbohydrates factor in. So there's all these other things that go together, but we can say that 74.3 of the variation is explained by the variation in fat content. The other 25.7% is explained by other things, okay? So that's pretty much how this interpretation of the coefficient of determination works.